Okay, next we have approximate or heuristic algorithms. This includes the Christoffels algorithm, which is a heuristic-based polynomial time near-optimal algorithm with approximation based on minimum spanning tree. Next, we have insertion algorithms like farthest, nearest, or greedy algorithms in practice, among which the best one is farthest. Then we have Google OR Tools, which is a highly optimized program that solves TSP by applying different heuristics such as simulated annealing, greedy descent, and etc. Then we have two-opt algorithm, where the heuristic is based on a move that replaces two edges to reduce the tool length, and similarly three edges for three-opt algorithm and LKH3 algorithm. We have the LKH3 algorithm, which is probably the best heuristic for solving TSP, and it's based on 2-opt and 3-opt with better way to select the edge candidates. Given a feasible TSP tool, which is a Hamiltonian cycle, the algorithm repeatedly performs exchanges that reduce the length of the current tool by replacing k number of edges until a tool is reached for which no exchange yields an improvement. This process may be repeated as many times from the initial tools generated in some randomized way. It generates near optimal solutions for symmetric TSPs, but some of the problems to be solved by LTH3 are best conceived as asymmetric problems, even if the costs are symmetric. Then we have the hierarchy of traditional TSP algorithms. Here we compare the approaches discussed so far. This diagram shows how the traditional approaches perform in terms of complexity, and to make the approaches feasible, we are required to compromise on the accuracy of our solution. On the rightmost, we have the naive approach of exhaustive search. This will give the optimal answer but will run in n factorial time, so it will become intraceable for n greater than 20. Similarly, the dynamic programming approach will become redundant as n exceeds 40. Next exact approach we have are the Concord and Gurobi, both of which are good only till n is in some thousands. Then time complexity decreases significantly as we leave the optimal solutions and allow some approximation with heuristic approaches like LTH3, Christoffels, and farthest insertion. Next off, we have application of deep learning in TSP. Deep learning has significantly improved computer vision, natural language processing, and speech recognition in the last decade by replacing handcrafted visual, text, and speech features by features learned from data. Therefore, we find it worthwhile to explore the application of deep learning techniques on combinatorial problems with the goal of discovering better heuristics than the ones handcrafted with decades of human research. TSP being a prevalent problem which has been researched for over 70 years makes it a good candidate to test the application of deep learning, and by its nature, developing an efficient DL solution for TSP might help develop similar deep learning based solutions for other NP-hard problems. The last 5 years have seen the emergence of promising techniques where graph neural networks have been capable of learning new combinatorial algorithms with supervised or reinforcement learning. Next, we have transformers. A transformers is a deep learning model that adopts the mechanism of self-attention, differentially weighing the significance of each part of the input data. Since its conception, the idea has been heavily used in the fields of NLP and computer vision. Like recurrent neural networks, transformers are designed to process sequential input data, such as natural language, with applications towards tasks such as translation and text summarization. However, unlike RNNs, transformers process the entire input all at once. The attention mechanism provides context for any position in the input sequence. For example, if the input data is a natural language sentence, the transformer does not have to process one word at a time. This allows for more parallelization than RNNs and therefore reduces training times. In the encoder, In the encoder, the input sentence is converted to a vector representation by translating each word to a vector while maintaining the context of the entire sentence using the attention mechanism. For example, meanings of words in an English sentence can change depending on the context, which is derived from the entire sentence. The decoder takes as input the vector representation formed by the encoder as well as the outputs generated by the decoder itself so far. Unlike the encoder's bidirectional self-attention, the decoder uses a unidirectional autoregressive masked self-attention, which means the inputs of one side of sequence are kept hidden from the decoder and the context is formed based only on the other side and the output so far. Thus, decoders offer great performance on prediction tasks like text generation. For example, in cases like text autocompletion, when predicting for the next word in the sentence, the decoder would have access to the representation of the English language itself formed by the encoder as well as the words input by the user and predicted by the decoder. Over to Vibhu.